For the team here, I just briefly want to give an introduction on who I am within Siemens, what we'll be talking about today for the sake of your time here spent this evening or morning, depending on where you're from. But predominantly, we're going to be talking about battery manufacturing engineering, specifically what mindset, ethos, or tenets you might need to have when you're going from a pilot line to mass production, specifically around the dynamism around those systems, your aggressive ramping needs, and then the future protections the team might need to have for, excuse me, rapid scaling. An introduction on myself. My name is Kyle Vugler. I am a technical account manager for Batteries US here. I am based in Troy, Michigan. I am also relatively new at Siemens. I've been here just over 2 months now. The reason I'm able to speak to this today is the last 4 years, I was the controls engineering manager for cell manufacturing at Tesla. My teams designed, deployed, commissioned, and ramped 10 gigawatt hours up in Fremont, California, as well as 30 in Austin, and then the design of the upcoming side, which I cannot disclose at this point in time. My time before Tesla was spent at ABB as a system integrator for 9 years. So I was a project lead for software and hardware design and commissioning for those systems for major automotive, aerospace, and food and beverage systems. But today I want to talk about what it looks like as we pull the veil off underneath it on the battery industry, specifically on engineering for the manufacturing ecosystem. Today, for my agenda, I want to talk about why it's dynamic and the rapid changes that are happening within the battery industry and how your engineering teams can overcome them for some best case use cases, as well as some things to take with you today. The iterative design, it is incredibly iterative when it comes to these new chemistries, new processes being rolled out from a lab today. It does take a while to deploy your manufacturing system, those changes tend to really affect production in the very short term. Aggressive ramping. Everyone right now is flush with cash in terms of deploying these gigafactories, but being able to navigate Death Valley for the next year or two to launch that program, it takes a lot when it comes from the pilot line design and proof of concept and series funding, all the way through to a quality cell at a high operational rate that's quality and usable. And then lastly, we'll talk about standardization and how that can enable you, or some of the key challenges you'll see in the early industry. And then lastly, scaling. So how can you actually design in aspects for scaling, which is what everyone's talking about, but I want to show you what it looks like under the hood. We'll skip over the question. This is Battery Day after all, and all the attendees, you are pretty familiar with the battery industry. So at risk of overly explaining something you already know, I want to at least set a baseline. Today we're going to talk about midstream battery, specifically from mixing through formation and aging. And my goal with this slide here is to really depict the different types of processes, the different key stakeholders within these different tools, as well as the different requirements that are required of them to be able to operate effectively. So we'll start here within mixing. So mixing, as I'm sure all of you are aware, that's where you're bringing in all of your materials, your dopants, whatever it might be, into an actual mixer and blending them together. In a wet process, which I'll speak to a wet process today because the dry process, there's only so few doing it, and I want to make sure I encapsulate the audience. For the wet process, we'll talk about a slurry aspect of this, and then sending that slurry over into a coating system, moving over into a compression or a calendaring system, slitting your mother roll into pancakes or whoppers, depending on your design for your process here. If you have a pouch or prismatic system, a folding or a stacking system, or a winding system for a cylindrical cell, as well as on the wet side, possibly a drying process, and then a filling of your electrolyte all the way through formation. The goal here, like I said, I really want to draw your attention to the battery industry. It is the battery industry, not the automotive industry, for a reason. It is really a Frankenstein's monster of 6 different industries, predominantly. That's the one thing I hope you do take away from this. It is food and beverage, it is life sciences, it is chemical facility and engineering, it is, we'll call it converting or roll-to-roll and web handling systems. It is going through high-speed discrete automation, typically within automotive and others, all the way through into logistics and massive ASRS systems, The only things that I typically don't see would be maybe aerospace design, minus some formation HVAC systems, or marine. I used to say nuclear until I found out some of these baghouses use uranium handling systems to have the glove boxes for bag break stations. What you're going to see here uh, in your electrode space, your mixing, coding, and calendaring, those are known as electrode these days. They are going to be rated environments and more so on a dry process. So when it comes to that dry process, you might have an atomized lithium or others or metal. So your operators would typically don a PAPR suit around these systems. They are rated spaces. The only exception would also possibly be an electrolyte. Where on the manufacturing floor, you typically won't see many operators on the day-to-day outside of loading and some minor material handling in the early days. Second to that is resiliency. So on the front end of the battery process, they are highly reliant and redundant systems. What I mean by that is in the discrete back end of automation, you can stop the process, reset cylinders, restart. When you have a fault or an error when it comes to powder handling or slurry systems or a web handling system, yes, you have to have that system for an e-stop to stop the machine, but rethreading the web is not fun. You're fighting gravity or momentum in these cases. So they require a high resiliency mechanism to them. You can't just stop powder from falling. You're fighting gravity. And plugging those systems and digging them out at 2 a.m. in the morning is not fun. Or rethreading the web at 4 in the morning is not fun. When it comes to this as well, material safety design, I'll briefly touch on this. It's not just purely operator safety when it comes to the manufacturing of these systems. There's definitely quality and safety involved, especially on the front end electrode. Not so much in the midstream, but more in the upstream of this. You get into 10,000 psi boilers, which is it's like a bomb waiting to go off. You get into some nitric acid handling and other aspects like this. Incredibly high operator safety, of course, but you also have a high level of safety for your product that you're building. We touched on it earlier, but the line side interactions, very minimal when it comes to electrode, but you will start to see that when they're moving material between machines as the system progresses. Discrete automation, if you're coming from automotive or aerospace or others, you can really lean into your strengths on the back end of battery manufacturing. The front end, like I said, is much more process automation, life sciences, food and beverage type of automation, as well as converting. And then high-speed precision motion. I'm going to be generalistic here, not speak to my alma mater and what their designs are there, but when you start to get into web handling within the battery industry, it is incredibly high speed. And you're doing 125 microsecond response times for your controls algorithms. It is not your age-old adage of 100 milliseconds for process. Parallelism I want to draw your attention to. So typically you would see an anode or cathode mixer feeding an individual line, the mother roll itself, to coat the line. Once you start to split the mother roll into different pancakes, you're allowed to add multiple different systems in parallel to process those machines, to handle that, to do your stacking and winding or whatever it might be. You will see far more automation and far more componentry on this end of the process. And then also facility reliance. This is another hallmark I want people to take away, and I do have a slide on this later, is these systems are incredibly integrated to facility and utility automation. It is not the typical automotive of, I need 200 amps, 2 RJ45 connections, and 4-bar compressed air. You need argon gas, you need chilled water, you need aspiration systems, you need life safety for fire suppression. A lot of these tools, what I tend to see people do is they will order them from whatever the OEM tool builder, they get them on the floor, they expect it to be a turnkey system. That is 60% of the game. Once those come together, integrating them together, tying them to facilities is an incredibly labor-intensive and incredibly important part of deploying these manufacturing lines. And I have a slide on that as well later. First, I want to talk about dynamic ecosystems. The one thing to note is things will change. On my deployments of cell manufacturing lines, I've gone through many, many recipes, many chemistries on what that looks like and what it needs to accommodate. And I don't see that changing for the foreseeable future in the near term. So how can you handle that? will be an important hallmark of what we'll talk about today. The number one thing in terms of stressors on your manufacturing engineers and your commissioning team is going to be the rapid scaling of a lot of brilliant people putting together a process, maybe a PhD holder, 20 people. It is a great process. Turning that and getting funding over the next 2 years into a massive, highly orchestrated workforce is incredibly difficult. With this multi-sourcing of tooling, I have yet to find one person or one company that can supply every single tool in cell manufacturing. You will be working with many different stakeholders, many different automation platforms, and getting them to play together is honestly an art form in and of itself. Second with that is scale-up issues. So being able to simulate virtually or doing certain, we'll call engineering tactics ahead of time, far more beneficial than we're just going to run this machine at different speeds, different rates, different deposit factors, and find out what our optimal cycle time or optimal rate is. Being able to do that is incredibly important, especially with an electrode. On anode, not so much. Graphite's pretty cheap. When you come to lithium, you're scrapping material that's quite expensive, and being able to do this is great for your OpEx and CapEx expenditures moving forward. The last two hallmarks here are iterative design changes, which I'm going to lean into in the next slide here. And then continuous uptime and tooling reliance. So like I said before, you're building a manufacturing line. You are not building a proof of concept pop-up shop to build batteries. Being able to make the system serviceable, long-term duration constraints, as well as work with facilities and other aspects that might change their process is incredibly important. What I want to depict here is the number one most important thing that I found for successful teams in deploying these systems. And it is keeping your head straight with all these different dynamic, multiple stakeholders playing a role into a highly connected system. I don't care what system you use. I'm here at Siemens. I'm going to talk about Teamcenter PLM, but the number one most important for being effective, the teams always have a bias for action. The second thing is they have a single source of information for where they're drawing their design decisions upon. So the one thing I want to have here is a chemistry or process direction massively changes a lot of the automation and the tooling on the floor. With that comes safety, and that is an effort to bring in safety engineers, process engineers, controls engineers, manufacturing engineers. Following this, you might have to change your automation strategy. I've had cases where the lab comes to me one day and says, oh, we don't need a binder anymore. So I have to turn off half my automation, and you can't just do that overnight. So how can you prepare for that? And then lastly, interplay between systems. Like I said earlier, commonly overlooked, tying these multiple different turnkey systems together is not usually foreseen for some reason. They need to work together. That is a number one important thing to keep in mind there. But being able to have a product lifecycle management tool to document, these are my throughput rates, this is my control narrative, this is my overall design for my system and my process and instrumentation diagram. Without this, it is an act of masochism, if you will. You have to have your teams work together off a single source of truth. That's what I want to drive home here. And this is how I want to depict that. Typically what you will see is most people talk about agile, and being able to do agile development of these systems, most teams just skip steps. That's how they actually create agile systems. In order to effectively do this without just skipping steps, you need your engineers or all your key stakeholders working on the deployment of that pilot line, mass production line, to work directly with your lab or your early process engineering teams. With that, which I draw over here is the waterfall telephone game. It will take too long with all these changes to come to you to be able to react in most cases. You're already on 2 versions behind by the time it gets to you. Being a tight-knit team, specifically for a controls engineer, you become best friends with process engineering, with your lab output of what they're doing on the coin cell validation, how that might affect you. And then as a effective controls engineer, knowing, okay, They're removing the binder, therefore I'm turning off all these different systems and I have to change all my routing. How's that going to affect my quality metrics? I have to turn off a bunch of alarms. How do I properly display that on the UI for operations and seeing their feedback, as well as turning off systems with facility that we no longer need to hold up a process if it's not operational? That is the number one thing you have to instill upon your workforce is being very collaborative, single source of truth, know what is coming from above them, as well as what their decisions, the ramifications are created from those teams. Here, I'm going to skip over it for the sake of time, but these are some of the key stakeholders you'll see on these manufacturing deployments, and they all tend to work straight from what's coming out of the lab. What are the core quality metrics? What is the core processor throughput rate? What are the safety concerns involved with this automation? Here I want to draw a depiction for what this looks like in reality. In most cases, people tend to view battery manufacturing as these individual tools on the floor. Yes, they have safety. Yes, they need to talk together to have a highly efficient system, but they're also extremely reliant on upstream, we'll call it the old adage of facilities automation. An example of this, in mixing, for example, when you have a dry process or pre-slurry wet process, you are moving almost explosive dusts and with a vacuum or a system here, and having an aspiration system that's typically controlled by facilities, incredibly important. You're not going to move that material unless you have an okay or a good to go from dust collection systems, aspiration systems. On the contrary to that, you might have chilled water. If you're doing a massive mixer, you might need to cool the jacket of that mixer. And if you don't have the proper temperature of that water, yes, it's a bad batch, but you're not going to hurt anyone. To turn that again on itself, when you're doing coating, you might have a defoaming agent or a solvent recovery system that has maybe an ammonia abatement system. You need to work with facilities to make sure that the damper for that displacement system is open. You cannot run that machine without that. So controls and manufacturing automation engineers in general, high integration with the process team, high integration with your facilities automation team, commonly overlooked. And then the last one is something like fire suppression. You're not going to charge and discharge without active fire suppression in your formation and aging rooms. I want to talk about next aggressive ramping and scaling and what that looks like in practice. Most of you may already know this or intuit this just by your understanding of the industry, but I want to drive a few things home. So in a pilot line, typically your automation scope is a factor of 12, 20 less than what you would see for mass production. You are incredibly reliant on an OEM tool builder because you don't know what you don't know just yet. Unless you're extremely vertically integrated and somehow you've already done this without doing it the first time, you will be very reliant on your OEM tool builders, their best practices, their quality metrics, their preferred software automation of their tooling. Your process definition is in the early stages of, yes, we think this is our optimal process, but you are about to learn far more. Tool interconnectedness, you can manually transfer material on a small sub 1 gigawatt facility. When you get a mass production, that really gets upended. And they don't really need to talk to each other. You're still in a pilot line. The data throughput, yes, you're doing quality metrics, but you're not doing massive data ingestion at this point in time. And then also time to commission, you're learning the first time how to commission these systems. Some of these might be, I don't know, we'll call it 10 meters tall, 100 meters long. With this, you don't just FAT this at a customer site and build it and ship it here. You tend to stick build them in some cases, especially in electrode for these massive machines. For mass production things, it is a whole new problem. It is not, I have 10 more of them, I'm in mass production. It is a whole new game. When it comes to this, yes, there is far more IO. You're going from 2,000 to 20,000 plus. Your teams being able to commission them, you still have a reliance on an OEM tool builder because one engineer cannot commission 20,000 IO in a day. So yes, you have them there, but at this point in time, you know what your customers provided, what you would like to optimize based on facilities, maintenance, safety, feedback from pilot lines. Your process definition definitely changes because at this point, automation is interconnected. So new problems arise there in terms of an okay to feed, an okay to receive handshakes. Does my batch system properly feed a continuous system now? That is a whole different problem. Shutting down this system is a cascade effect upstream. Um, your data, massive amounts of data come from mass production. Being able to turn data into knowledge is another art form that starts to arise when it comes to mass production on predictive maintenance and optimizing your throughput. Time to commission, it still goes down. It's mostly reusable if you do it correctly, but at this point in time, they're just so large, you still have the same problem that you once did. When it comes to this, I want to take a moment to talk about workforce. I know they talked about this just a minute ago, actually, in the main stage, but workforce for your OEM tool builders and your system integrators is incredibly important. And the pilot line, you might receive 7 different PLC platforms from 7 different companies because they are the ones who know that in the industry. We're still a very early, immature industry, we'll call it in the US for some cases. Knowing that your workforce in Asia might be very proficient in Mitsubishi and Omron, they have the task to deliver fast, to deliver what you need in a reliable, well-informed manner. But as an end supplier or an integrator, knowing that your workforce in the US knows Siemens, Rockwell, Beckhoff, things like this much better. How can you hire people to support those? And how can you instill that platform on a workforce that isn't proficient with this? That is typically where Siemens really helps work with the end customer as well as OEM tool builders in Korea. Our team is global and we understand the design requirements and how we can support them from the tool builder side of things. We also have a significant Siemens C-Train offering for a lot of those different companies. The next one, I think I'm going to gloss over for the sake of time here, but within Siemens, we have a massive amount of industry knowledge on the battery industry specifically, whether this be our worldwide standards for CE versus US regulations and NFPA, as well as our preferred hardware list, preferred software templates that we've built for the battery industry, guidelines and specifications for application-specific technical aspects, whether it be the process, the safety implementation, or how we use it, training and workshops on-site, remotely for your team, as well as consulting and support. I think people tend to overlook as well. Siemens is a very big company that can do from feed stage to implementation, commissioning. Siemens can support through the whole life cycle when it comes to this. Very important for the US industry, I would say as well. Like I said, very brilliant people, heavy funding. They might not have 100 years of experience of tenured, standardized industrial automation engineers. They're going to be looking for people to support them. I want to draw a few aspects here of what that looks like in practice. So in terms of standardization, Siemens, my team, we've been building out preferred hardware lists to be used on the automation that can survive in these environments, that can run at the speeds that these need to achieve. Templates, a big one in terms of moving into the battery industry. You're blending discrete and process automation. So how do you articulate that on a screen? How does an operator effectively use this in 2 clicks or less? Using modularity in your code development is really big in terms of, I want to do 1 gigawatt, I'm going to expand to 10 and then to 100. All of that capital investment you're laying down, you want to be able to reuse that and iterate upon it and build upon it. So how can you do your software development in a modular fashion to not reinvent the wheel for every production line? Within Siemens, extensive understanding of those. So like I said here, we have Ops Center, PLM, IoT. The list goes on for preventative maintenance and operations and manufacturing. Simulation, I'll touch upon in a second. A really big help in going from pilot to mass production, and a plethora of use cases that we can share that are non-NDA constrained. Templates for doing your due diligence ahead of time, templates for selecting the right hardware, doing your simulations, and then also in terms of connecting to multiple different platforms to one aggregation system. I want to show you an example of maybe what modularity would look like in practice. So here is a extremely brief 10,000 foot view of what you might see in mixing, for example. You might see a PLC, you have some motion control, you have some load cells for your gain and weight, loss and weight into a dosing system or to a mixer. You also have a lot of process automation when it comes to that world, high analog, less digital. The one thing to note here is a tool provider might only provide mixing, they might not provide coding. And then even if they do provide mixing, have a monolithic structure is a very big detriment, because if you want to service a portion of this or run a portion of it without the other portion, it's really good to know about hot swappable I/O, your span of control for your PLCs, and the modular nature for what you can reuse and use. And I'll show you more in a second on that. The big thing right now, it is very hard to walk the walk and talk the talk on this, but people doing it are seeing massive dividends on what their work looks like. The modular production aspect. Now, how does this help everyone in the industry? One, for manufacturers, it is really good to be able to have a modular system for A/B testing, for scaling for the future. Like, yes, this system worked, the system didn't. Go with this one. We're going to move that on. It's not one system tied together that you have to redesign. A second, for line integrators, if you have multiple different platforms, multiple different parts of the world, different platforms, how do you break them up in a modular fashion to interchange and swap them out? Also, for the end customer, it is a big help in terms of quick adaptation for changes on the floor. You can change a certain portion of your system, not rewrite a bunch of code for massive monolithic structures. Now, what does this look like in practice? This is what it would look like. So this is a subset of modular breakdown into mixing. You would see something like batch handling be on a separate control strategy from your mixer. The reason that it's helpful is you might have a new mixer one day, and I'll speak this in a second, or you want to do maintenance on a mixer. You want to still be able to run production on your upstream. You can take down one system, let maintenance do whatever you want, deploy new code. You're only affecting a portion of your operation. And being able to have multiple different control systems allows you to do that. If it's one, you're going to turn off, lock out, and the whole thing is down. You're sitting there waiting for them to apply them. Also, when you want to make a change on automation for mixing, you don't really want to expose risk to your upstream process that's been running really good. As you start to scale, this becomes far more valuable. And what I mean by that is, based on my alma mater, when I would go into mass production, you will find the limiting factor of what OEM tool builders can build in a singular year. You're not buying one mixer, you're buying 90 mixers, and they're huge. They're 1,000 horsepower plus 90 mixers. You will find quickly that being able to adapt to 7 different suppliers to build you the exact same tool is incredibly hard. So having a modular code you can give them as a reference, or being able to own that within your own organization to say, give us the hardware, we'll write the software because we have to talk to everyone. That is a massive leg up when it comes to the mass production adoption. Being able to source from multiple vendors to deliver the same tool because they can only build so many a year is a common, almost on every tool, problem that you're going to be seeing in the near future. Next, I want to talk about simulation real quick before we tie this up. I won't speak too much to this because this is a PDF and you can't see the fancy videos, but it's incredibly important for understanding what pilot to mass looks like for your roadmap. So within Siemens, we have a litany of software and simulation capabilities. I want to draw your attention to a few, and forgive me, you can't see all the fancy moving bits of this slide deck. In mixing, you may see you need to do, we'll call it high speed vibration tests, and maybe why the blades on your mixer is vibrating and how can we effectively run this. You might just need to look at distribution within the mixer. Being able to simulate this is incredibly important. As you step forward into coding, being able to coat and then check with maybe a thickness gauge on your web is great. Being able to simulate this with multi-physics ahead of time will save you massive amounts of lithium scrap as you run. You're not doing trials and measuring with closed loop control. You're actually virtually doing this with no cost to material or scrap rates as you ramp. Same thing with calendaring. That is a big portion of quality in cell manufacturing. Maintaining your electrode thickness, being able to simulate down to the actual particle physics of these systems Siemens has done and will continue to do to support systems here. As you get into more complex aspects of these systems, discrete element modeling, laminar resolve modeling, and slurry modeling, these become incredibly important for throughput calculations, incredibly important for why is my machine not running the way it's designed to, as well as simple changes like the moisture within a room will affect the particle physics of the powder or a slurry moving through a system. It might aggregate on the walls and kind of just go right through the middle. Being able to simulate your limiting factors and what can and cannot be done, very important. As you move into slitting and onward, that is one unit piece of material you're going to be building on top of. When you're doing mass or bulk solids handling up ahead of time, being able to simulate is incredibly important. Trust me, I've tried radiating materials to trace them and look for it. Simulation is the only true way to look at your probability of where is that piece of powder or that piece of that element, where is that within my process? Being able to do that with the probability and traceability and genealogy and build that out is incredibly helpful. Also, if you're starting to scale your mixer into a larger size, how does my distribution within my mixer look, or my load quantities? The last one here, you really can't see too much because it's not an animation. After this, hopefully I can share my PowerPoint so you guys can all see this. Being able to virtually simulate within Siemens your PLC runtime, your user interface, and then also its feedback for the simulation event, incredibly helpful. Yes, it is a lot of work to set up in the very beginning. I won't deny that. It is incredibly helpful for tool builders to do a virtual buy-off. Does my safety system work the way it is before a customer comes on site to buy my machine? Being able to see, if I add 10 more pallets to my line, what is my new throughput limiter? Where's my bottleneck now? Within Siemens, the capability tied directly to your PLC control environment to emulate a PLC, to emulate the multi-physics, to emulate the cause and effect responses, incredibly helpful. The last thing you want to do is have 10 engineers from an end customer standing on your floor to do a buy-off. You could have done that ahead of time. They're just going to tear you apart for nitpicky labels and colors and things like this on your tool. Being able to do this, incredibly helpful.
Kyle, actually,
Especially as you go
2 more minutes to conclude. Sorry to disturb
production,
you.
when you integrate this together, you need to know how they're going to be working together in real life instead of learning that on the floor, which I've done. It's not fun. This is one thing I wish I had about 4 years ago. With this, you can't see the animations as well. Being able to, in the web handling portion of cell manufacturing, alter your dynamics for web handling, incredibly important as well. Tension is the name of the game, web alignment is the name of the game, and limit defects, name of the game. Being able to move those different servos and simulate the optimal speed at which the position offset, how that affects your tension. If you're doing a dry process, you're handling an electrode without a foil, incredibly hard to validate those tensions without actually doing it in real life. Being able to simulate it now, incredibly helpful for scrap reduction and ramping. As you go into the wet process, still very important, still incredibly important for optimizing cycle time. As you expand 20 times larger, 1 second is now half a minute. It's a very big deal on your output and throughput rate. Also within this full 2D, 3D, built-in PNID simulation capabilities within Siemens to do this. Like I said, it is incredibly important as you go to mass scale. Working at a pilot line speed of maybe 80 meters a minute, great. When you start to go into 500 meters a minute in high-speed dry processes, you almost don't have time to respond on the tool itself. You have to do these things virtually for marking and non-marking because the web's just gone at this point in time. Being able to simulate what that will look like in practice and does your data flow the way it needs to, incredibly highly important for your controls engineers. Lastly, within Siemens, this is my boilerplate slide here. Smart infrastructure, so designing the system to be able to support the massive integration for the floor. Our digital industry is well known in the system here, motion control, safety, motion and controls. digital industry software. So that's the simulation portion I talked about here. It can be full plant throughput design and material flow, all the way down to multi-physics, particle size, and friction coefficients. Lastly, 8 out of the top battery suppliers are using Siemens today. There's a few I can't talk about that are using us as well. And this is me. What I want to do now is I want to open it up to questions, comments. I know time ran over on the main stage, so we're kind of feeling the effects here.